Hello everybody and welcome to my first video of my new Redstone computer, built in Minecraft of course, and you've probably read the title here. I apologise for my lag here, but it's quite a large world. Okay, it's quite a bit better. I did get a mod installed that allowed me to freeze all ticks, which meant no lag while building. But if I actually want it to work, then I can't have that activated. But here, this is the computer. So we have the main motherboard here, full of all its beautiful components. Here we've got a tester, which tests whether data is larger, smaller, or equal to another section of data put into it. This over here is a program counter, program memory, a subtractor, a adder, all of the control circuits for that. Then we have over here these four little things here. 1, 2, 3, 4. They are all caches, so we have 4 main computer caches. Then this here, the block here, and some more throughout this, and there's some more under here, but you might not be able to see it. There we are. That is all control for the random access memory, or RAM, and I am now stuck. Oh, wow, this is looking quite a bit. It's lagging more than when I was actually building for some reason. That is because of my recording software. So here is the RAM. It's a pretty compact version of RAM. I did have 4 times as much as this stacked on top of each other, and I can have a lot more RAM and still be able to access every bit of it. But each one of these wafers here is 16 bits, so it is 2 bytes worth of RAM. Since the computer is all 16 bits, I need each one of these to store a command or a section of data and its address. If I wanted to, I could probably make these dual function, because you don't need to store a full 16-bit command. You can just store it in 2 segments of 8-bit, which is how the principle of this computer works, making it like twice as powerful with a very small instruction set. I say very small. It's still quite large. So here it is actually a dual core computer, as I probably put in the video title. So each one of these sticks here is actually a core of the computer, and I just figured out I can stop the lag temporarily by pausing the clock. Oh, that is better. Okay, so each one of these sticks here is a core. So we have the stick running up here, that is the first/main core, and then we got the second core. As you can see, each one has 2 cables that are quite different. So the input cable for core 1 actually comes off 2, so it comes off the main core line, which is the main input for this core, and that will only be allowed if core 1 is full. So that's an overflow system. If somebody writes a user command and program memory wants to run a command on the same clock cycle, it can handle that by outputting it to the second core, which will run it along a different command bus. Now you must be thinking, they're all outputting onto different cables. How are you managing to only have one set of each component? That's because each one has its own access line to a specific component. So the output lines on, and sorry if this is getting a little bit technical, if you want to get to like less technical stuff and just the actual demonstration, then skip ahead probably about a couple of minutes, like 1 or 2 minutes, and because I'm going to go to some demonstrations then. So this is output line for core 2, output line for core 1. They're going on to different sections on the bus. And that's because if you want to access 2 components on the same clock cycle, you can't have one output bus, because the signals will get mingled and it'll end up coming out as neither of them. So if we go to just any specific component, here we are. So this is the this is the program counter. So if you want to send a value to the program counter that it will then add 1 to, it comes along here. So we have our core 1 output and our core 2 output. They get combined in this circuit, which is called a combiner. So it will take one or the other value and it will just combine it into it, and that won't travel back through either of the lines. So if both of them do happen to be on, so you're trying to run exactly the same command, then things get a little bit screwy. But I could always just redesign that gate to only allow one of them through. I was just being a little bit lazy there. But even if it did that, it would still run the correct command. It would just combine the data. So if we now take a look at, well, this is exactly the same thing. So it combines the input, exactly the same two inputs in two gates. I probably could have just used the output from one of them and then run it through all of them, but that was too easy, and I'd already built this system. So it combines the two inputs, outputs it to one cable there, outputs it to another cable here. This is a tester, so it'll test for the binary values 0 to 15 and convert them to decimal, which will then output to this cable. Then this blue cable is corresponding to the command that will allow this gate to be open and send through the whole of the command that triggered it. So it will send through that command. So these 3 gates and 1 bus transceiver basically decode the command and its section of data. So if the command on the 16-bit data, so there'll be an 8-bit section at the beginning of the data that will be triggered, allowing the other 8 parts, so the secondary 8-part bit of data, which is the actual data segment of the 16-bit input, to travel through here. It will also allow the command through, so you still get the full 16-bit command coming through here and loading into this automatic register. So this is a testing, so it will test for any 1 on all of the 16 bits, and it will just output a signal. These are simply repeaters for bus input, so they have a repeater inside them that repeats all 16 of them and delays it slightly. So these two will add up to a delay long enough for this signal to come here, flip this, which flips this, allowing the 16-bit input through here, and it will wait in here for a second while this one then closes before it gets rammed into this one, and then it will save it in this bus transceiver with the input, and then this will flick as soon as this is no longer detecting an input. Excellent. Then that's just being inputted into this program counter, which is basically just an adder, but where instead of having 2 inputs, so instead of having 2 caches, it just has a 1 constantly being added in. And then it will constantly output to here, and when you want to retrieve the output, you simply send a command. Well, actually this one doesn't have a retrieve function because it's a program counter. It just gets used in program memory to select whichever wafer you want. Program memory is pretty interesting. Each one of these holds a 16-bit piece of information that can be read at will. I haven't actually programmed any of this, but you manually program it here. So it doesn't have a write function because it's not RAM and it's not a hard drive. It is literally just program memory, so you can read it at will. But you can read every single one of these. So this is, each one of these is 16 bits, and each one of these is, what are they, 15 long? Yeah, they're only 15 long. You can make them as long as you want, however it would require some extra circuitry because of these selecting. You can toggle them on and off and so forth, and every time they reach the end they will automatically close themselves. So they will run, so as you send the command through here to run whichever one you want. So I'm only using 4 out of a possible 256 lines of this, and each one of them can be up to 256 long. So it's a ridiculous amount of program memory, but I didn't want to put all of that in. So it will select it, then it will automatically start up the read and return function, which will be every time it detects an output, it will send this to the program counter, which will automatically recount and add an extra 1. So it will take the current output and it will put it through into the input section, which will add an extra 1 to it, and that will do that once every clock cycle. So that's the problem that I entered with the 2 cores. What if there is a push function which requires 2 clock cycles, or a read RAM function which requires 2 clock cycles? Actually no, a read RAM cycle only requires 1 clock cycle, and it's the write to RAM which requires 2 clock cycles because you need to open a RAM cell and then you need to send the data to it. So that requires 2 clock cycles. I haven't actually managed to get it down to 1 clock cycle yet because the it's simply not big enough. I guess if I worked it like the GPU I might be able to do it, but that would significantly reduce the amount of RAM I was able to have. But anyway, yeah, this is the GPU. It's still a work in progress. I'm not sure I can really call it a GPU yet. It's more like a graphics output unit. It simply converts the graphics into the medium used by the displays. This is actually I'm pretty proud of this. I mean, it's in its infancy, but it's an RGB display, so a red, green or blue display, and it's 12 by 8 pixels. So a pixel is denoted as these 4. So it can either be blue, red, or green, and you can display that for all of them. And what I like about it is you control 4 pixels using only one command, and you can send it to the screen. So I will demonstrate now. Let's get on to the demonstrations. So I'll explain the displays quickly. This is the middle section. For some reason it's the input, so I can either directly input binary, because that's needed to control the graphics display unit. A binary input, you can't input a decimal because you can't get the control over the binary digits without doing some complex calculations. This is the decimal input display, so it's a 4-digit decimal input display, and this gets converted into binary and outputted in the correct format using this logic gate. And then this is the binary output and a decimal output. The decimal output doesn't work currently. I'm still working. Well, it works from numbers 0 to 9. Any more than that, and it will just not output anything, which kind of sucks. Actually, no, it should output all the bits that are corresponding to the 1 to 9 on any input sent to it. But it does technically work. This just outputs the binary of whatever you send to it, including the command. That's the binary input, decimal input, and the RGB output. So for some reason input is in the middle. But anyway, let's get on to the display. That's my Blueprints development center. I'll just take a quick peek in here. Blueprints, they've just got all my blueprints for all the different integrated circuits that I've used. They're all named using bases and stuff. It's interesting. So we got a very small input display, which is nice. It's all computed over there, and I'm not sure I'm loading the entire thing. I should probably click my render distance up a little bit, and let's just make sure everything is loaded. I probably also need to oh yeah, it was not loaded. That would have been a problem. That would have been a big problem. So I'm going to unpause the clock. You can actually remotely pause the clock from the user station, and you can step through as well. So you can step the clock. You can just clock cycle it 1. There's the pause command. This is mostly just for GPU inputs. Right, okay, so we've got a clear display currently. That selects what piece it is on, and you can move this using this function to the 4 different bits, which means you can edit it even once it's in there. The clear function will just reset it back to the beginning. So if I want to input a oh damn it, I need the command book. I can't remember it off by heart. There's 26 different commands. I've got the big books mod. I should probably take a duplicate of that just to make sure I don't lose it. But here is the command book. Dink. So let's go to the basic, all the basic commands. That's not a command structure. So I haven't added command 25 and 26, which is the GPU control. I should probably add that. And then there's the GPU, which is 128, which means my total instruction set can only be 126 commands rather than 256, because the GPU takes away half of those, because I needed the full access to 16 bits of its command data. But anyway, so we have our basic controls. So if I want to just send, let's send adder cache 1. And then we'll send it a piece of data. I'll explain how that works. So we want to put the command first, so we want to put a 9 in. So it doesn't matter which one of the 2 blue slots the 9 is put in. And then we want to select a piece of data. So we're going to send it a... let's send it a 7. So if we put... so we're sending cache 1, I believe. 9. Well, no, we're sending adder cache 1. A 9. That's how the command structure works. It does detail how different sections. So this explains the command structure. This explains the GPU, and this just details the basic, all the basic commands that you can add. So when we enter that, the display will automatically get cleared, and it should have performed our function in the GPU. So if we go and have a look at adder cache 1, it should have loaded the value of 7. Here we are, there we are, there's a 7 in the first 8 bits of that, and there was the command that brought it to it, which is a 9. As you'll see, the 7 is now at the front, so it's currently inputting a 7 into here. There we are, and it's outputting a 7 as well, because there is 0 being added to it. So it's currently doing that, but it's not outputting it just randomly into the computer at the moment. So what we can do is send something to adder cache 2, which is a 10. So now's when we make use of the fact that we have multiple digit decimal entries, which it took me a little while to come up with, but I didn't actually do it in this computer. So we got a 10 there, and if we send a 1, so we're going to send a 1 into adder cache 2, click, and this computer is very fast as well. This clock cycle may look pretty slow, but it completes functions very fast. So there we are, we have sent a 1 into this cache. Boom. I mean, you can't actually enter something with the clock on and get to the computer fast enough to see the function being carried out. It does each function in under a second. So it's a lot better than most other computers out there. And if you want to increase that, you can overclock the clock. However, if you increase the clock speed too much, it won't finish doing a function before it attempts to do the next one, which can become an issue. That's based on all the cache systems involved. So right now, if we want to get the value that we've just done, we look through here and we go push the adder result to a location. So we can push adder 1, which is a 11. So we put an 11 command in here. 11, and now we're going to want to choose a location. So a location needs to be selected from the send options. So we can send it actually to, we could send it to 25, which may not be listed here. However, that will output it on the binary display here. So now we simply write a 2. I haven't actually tested this, so this will be a first time, but I've tested all the individual components. So we send it to a 25. So this will basically push what is in the adder result cache currently, and it will zip it into the core, which will go into core 1, and the core 1 will then look at this instruction, so the 25, and it will route it according to this command book. So the 25 here will send it then to the GPU, which will send it to this binary output display. Hopefully. I'm very much hoping this works. If this doesn't work, I'm going to cry. Hey, there we are, and it will have sent the result, which is an 8. We look at the bottom row here. So that was a 7 plus 1 is an 8. Now that actually took 2 clock cycles to perform, because we had to wait for 1 clock cycle to take it out of the adder, and we had to wait for the next clock cycle to put it into that cache. So what we will also see happen here is none of the inputs in the adder 1 will have actually changed. So we've still got a 7 technically in this cache, because we've still got a 7 plus 1 being added. However, now if we want to do something very clever, that value is not there anymore. However, we can push the adder cache. So if we take, it's an 11, so we take another 11. I need to move this next button somewhere. We'll put an automatic next function whenever a button is pressed. I can actually do that. I simply put a tester here, and it will send one into there. Oh my god, that is such a good way of doing things. This is going to end up being, I won't make this video too much longer. I'll go into more detail in the next video for anyone who actually wants to know how this piece works a little bit more. I'll do an individual component tutorial. But anyway, so now we want to put this back into, so we send adder cache 1 the 7. So we want to put this into 9. Think, and this will put it back into the adder, which will now should be yielding a result of 9 instead of 8. So we're going to see that one get an extra 1 on there. So it'll be that input, but with that on there. So when we actually enter the correct command. So we want an 11. An 11, and then we want a 25. And that should push the value there to a 9, it should hopefully. Boom! Excellent, that is beautiful. So there it is, and I'm just going to quickly there's just a 1 on there, something's already loaded into the cache. So I'm just going to quickly send something to the GPU. So GPU command on. I'm now going to be looking at this, and it shows that the GPU command is on, which means it's using the second control circuit to enter binary, which means it doesn't need to do any of the really complex conversions. So we're going to want to send it to, it's all detailed in here, 120. So you have a look at the GPU and it will explain the command structure here. But I won't go into too much of that now, but I'm simply going to send it to row 1. Actually, that will be that tile, so the bottom right hand corner of the screen is detailed by that. And I'm going to send it a red, green, blue, red. So that's the code for each one of them individual cells. So it will come up as a red, a green, a blue, and then a red, I believe. I think. Enter. That will also get cleared whenever you press enter. I'm pretty sure I entered that command right. I've been messing around with the GPU lately. Let's try a 128. And then let's just output 4 blue squares. Enter. It's very strange. Very strange. And why is there a random orange segment lit up here? Ah. Damn it, why doesn't that work? Yeah, I'm just doing a little bit of debugging here. Dink and dink. That should stop that from going out through there. Okay, so unfortunately the RGB display isn't working, but all the other functions are working in the computer, and you can program memory to run a set of commands, so you don't need to do this every single time. But this was the first test I've done with this actual output before I had to go around and look at all of the different components. But it's pretty fast, and if anybody else would like me to create a program to run to test it, and when I do finally come up with something that's completely usable, I do plan on putting a world download on YouTube. This will be my first proper video. I've done about 6 different iterations of this computer, one of which is sitting far over there. This is the first one that has really worked on this principle. I've been trying to get this principle to work for ages, and I haven't actually fully tested out the dual core system yet. However, this is the first dual core system that I've really seen on Minecraft computers, or at least Red Power computers, that works properly how it should. Other people simply create a duplicate of that whole system and stick it above, which is not efficient. I mean, sure, you can technically class it. You should really call it a dual computer, because it doesn't just have 2 cores, aka command decoding centers, which is what I do. Mine don't technically decode the command, they simply route the command. They control the flow of data on 2 different routes, meaning you can have twice as much data flow around as you normally can. But this lever is on. That's probably not helping my lag. Constantly running this small little command circuit here. That's just my tester for every piece of command that I run there. I was trying to develop smaller cores that I can make look really fancy, but at the moment, I mean, cores don't look very fancy. I'm also developing an I/O port here, so this is currently input. This will be output and input for extra devices that people want to register. But currently, yeah, these cores don't look particularly flashy. I mean, all they do is take a clock input, a couple of user inputs. They can be manually cleared with these levers to make sure there's nothing in these caches. Yes, excellent. Right, thank you for watching. If any, thank you all. Sorry the RGB didn't display for some reason. I'm gonna have to go and have a bloody look at that now. Why the hell is that not displaying? It's very strange. It should. It was working about 15 minutes ago when I was testing it. Maybe if I try different, I'll try one more. So 428. I'm going to turn off the GPU command and just manually input 128 that's required. And then I'm just going to just input that. I'm beginning to wonder now, actually. I mean, this has a massive ribbon cable to control this. Comes in here. Do I accidentally blocked something off when I was making the decimal output? It's a shame world that it doesn't work with shit. There goes the mic. This is the control for the RGB screen. Nothing looks like it's broken. Well, that's really weird. But anyway, thank you for watching. I'm also pretty pleased with how this looks as well. You just got the one bus going up and down, and then all the components feeding off the RAM outputs. But yes, thank you very much for watching. I hope you all enjoyed seeing this video. I plan on programming it with some more complex programs very soon, but use the actual tester and subtractor with the program counter. They all look the same, admittedly, except for this one. This was a lot of work to make work. It's that whole section there that controls the tester. I'm pretty sure it works because it can return the biggest value, the smallest value. It can test whether a value is bigger or smaller, or if it is the same, and it can do this all using as fewer commands as possible. I mean, literally. Have a look at this tester. So tester 1 there. So it uses 19, 23, 4, 5, so it uses 5 commands, which is admittedly a lot more than any of the other components use. The RAM only has 3 commands. But yeah, it's very, very, very good. Thank you for watching. I'm pulling out this exit here now. Anyway, yeah, thank you all for watching, and I will see you later. Exit from the Demonde Redstone ePig. I'm sitting here by the program clock. Goodbye for now. Ciao, ciao.